Okay, can you hear me? Okay, so today we are going to talk about deductions, finally. So that's again the plan. Tomorrow we will talk about a bit more about multi-messenger, but let's focus today about the actual deduction that we have. So to summarize a little bit what we have done till now, we said that we have different sources, potential sources of gravitational waves, and the only system that we discovered are binary black hole, binary neutron star, and binaries of composed of a black hole and a neutron star. And we have seen also that these type of transients are well detected by both matched filter analysis and unmodeled analysis. Of course, there are plenty more other types of analysis, but I just highlight the fundamental ones. We have seen the shape of the waveforms, and now it varies with the change of the masses and the spins. And so we have the spiral phase, the merger phase, and the ring down. From each of these part of the waveform, we can gain some interesting information about the binary system. Let me see if this worked today. No, it doesn't. Okay. So that's the explanation of how our matcher filter works. So what we have is a template that is as huge as possible and covers a huge parameter space according to the model that we want to prove. And so we have a simulation of binary neutron star that are the one with the primary and the secondary mass that are smaller than few solar masses. Then we have the region in which we have the neutron star and the black hole, so one mass is extremely higher usually than the other one. And then we have the simulation in which we have the majority of our deductions about binary black holes. We have seen that the gravitational waveform change with the mass, with the spin, with the orbital parameters, and so we will see some of these interesting details today. So let me start with the first ever deduction of gravitational waves. So that's the simulation of what really happened and on how the time space is curved. And at the bottom you have the actual waveform. So when the times goes on, you will see this waveform becoming blue, and so you will see the exact match of the waveform with the system that is coalescing and then merging. So you see, if you remember this first ever deduction that we had a binary black hole system of one was 36 solar masses, the other one was 29 solar masses, so a pretty equal mass. And you see that how the mass wrapped the space-time, as we said, like a rubber sheet. And so here you see the spiral phase in which the two black holes are orbiting each other. Then you will see a moment in which everything is frozen, and then they will merge, producing the gravitational, the emission of the gravitational waves, and that's exactly what you see down on the bottom part of the simulation. And by the time the two objects coalesce, what you have is the ring down phase in which they have to find a new equilibrium, and so they also release a huge amount of energy. Okay, so what did we actually see in the detector? So we said that the output of each interferometer is a time series. So this is the actual data in the Livingston interferometer. And this is the one in Hanford. These are data, okay? Time series. Now I'm going to superimpose the prediction coming from theory. Take a look. It's impressive how the match of the prediction and the waveform that was reconstructed is high. In fact, what you used to say is that this we didn't believe in this event because it was too close to the textbook. Okay. So this is the these are the two waveforms detected in the LIGO detector, Livingston and Hanford superimpose. And this is, let's see if you can hear the whip today. Maybe not. Can you? Okay, good. So that was the whoop that is defining the chirp, that is this structure that you see in the time frequency plot. That is really the feature that you're looking for when there is a binary system that is coalescing. Okay. So, excuse me. So this is the waveform that we reconstructed, and you see this is the inspiral phase. They are getting closer and closer, and then there is the merger phase, and there is the ring down. What I want you to pay attention on is the lower plot. That always amazes me. So what you have here is velocity in terms of light velocity and time in seconds. So when these two massive objects, around 30 solar masses, were spiraling each other, their velocity, so their speed, was half of the speed of light. Can you imagine something like that? I mean, it's amazing. They were really spiraling each other out with a crazy amount of energy and also speed. And the other thing that is interesting is the amount of energy that was released in gravitational waves. So when there is a coalescence between two compact objects, the sum, the resulting object is not the sum of the two masses. What's missing is the energy that is released in gravitational waves. And in this case was order of 3 solar masses. So it was a huge amount of energy. And of course, when you get a detection like this and that you're working on since years, and yesterday we have seen that we wait this for 40 years, people start getting crazy. And so what happened after the release of the news was that people start advertisement statement in New York saying that that it was easier to find a gravitational wave than an apartment to rent, or you can actually buy a dress that has all the signature of the first gravitational wave in different color on it. So people behave in a different way according to the environment. So what happened after? So we released the announce. So a GCN went out with the fact that we have detected for the first time a gravitational wave coming from a compact object. As we have said yesterday, the problem was that the first detection was made only by 2 detectors, the LIGO detectors. And so you remember those elongated error regions that we have seen yesterday in the sky region. That's exactly what happened in this case. So we had a huge, you can see here, a huge error region, order of 1,000 square degrees, associated with the position of the first ever detection. And so it was practically impossible for telescope to cover in a reasonable amount of time the whole sky. So what they decided to do, we are talking about 25 different teams between telescope and other kind of detectors. So what they did was to patch up this error region and divide this between them in a way that they can cover more error region to see if there was any transient or kind of other kind of sources associated with this event. Unfortunately, in this case, nothing came out, and so we didn't find any additional association with the detection of this particular event. But that was a good training to start and also increase the amount of people and groups and the type of detectors that wanted to follow up the gravitational wave events. So this was the first run. You see O1 stands for observing run, so the first observing run. So this is the first ever detected gravitational waves. Then we had a candidate that we said that if it's a candidate and it doesn't arrive to be a signal, so an actual detection is because it doesn't arrive to a certain threshold, that is the 5 sigma that we said yesterday. And then there was another event in this run that we call the Boxing Day, because it was the December 26, 2015. And even in this case, you see, this is the candidate. So you see the naming is different, LVT, and then the date. But also for the second event, that again was a binary black hole coalescence. So you see that there is a dichotomy of the two error regions. So there is a degeneracy because with the third detector we can pinpoint the position and also reduce the error region associated to that position. But with two, it's pretty hard. It's not possible to do that. And here you have the amount of square degrees associated with each of these signals. And so you see, you go from 230 to 1,600 degrees squared. And as we said yesterday, in the case of the addition of Virgo, that would be reduced by a factor of 2 or 6, between 2 and 6. Now we will see in another plot what does it mean. So what you have in model search, so the one that we covered the other day, is that so you have this plot that show you the number of events over the statistics. So this is coming from match filtering, and this is coming from a model search. What is different is the statistic. In the right case is the likelihood, as we said yesterday, and in the other case, it's another statistic, is rho, that is proportional to the SNR. Anyway, the point is exactly the same. What you have here in black is the background that you expected from the search, and these points are the search point, the orange one. And you see, as far as you can go to this black line, better is the detection that you will have. And so you see the GW 150914, it's over here. This means that the threshold of phi sigma was reached, and so we could claim the detection. And it's exactly the same with the second event, the Boxing Day, that is over here. So again, you see the background that you expected from such kind of search, and then you superimpose the points in which you detected something. And so going so far away from the background means that you have an outlier. And so that outlier, if the statistic is telling you that the threshold is more than 5 sigma, is definitely a detection. That's doesn't work as well. Okay, so this is just to show you that if you do the same exercise with the unmodeled search, you remember I talked about coherent wave bust, that is the first analysis that actually spotted the first event, and it's not a matched filter analysis. The statistic is different because it varies from pipeline to pipeline, but the concept is the same. So you have the number of events, you have the background, and the event is really an outlier of the distribution. Okay, so we said that when you finally get the detection of a gravitational wave, you can constrain different parameters. We said that some of the parameters are intrinsic, some are extrinsic. For a binary black hole, these are 15 parameters. With a binary neutron star, we have 2 more because we have to consider also the tidal force of these objects. It is really convenient for us to give this information as the chirp mass, for example, that is this combination of the primary and the secondary mass. Of course, the total mass, the ratio of the 2 masses. Then you have, of course, the spins and how they are aligned, and also the luminosity distance, so the distance at which you were able to detect such event. This one is just for the first observing run. So you see the difference in the masses, but what I wanted to highlight that I said at the beginning was the amount of energy radiated during the first event. That was 3 solar masses, and this is the corresponding peak luminosity that we got. So this is another view of the sky. With the first 2 detections, the candidate, and the first detection. This is the first detection of the second observing run. And you see also in this illustration, you can see how wide is the error region associated to each of these detections. So the question was, if Virgo was online at the time, what will happen? This. So you will not have anymore the degeneracy of the 2 error box associated with the same event. You will have a single error box, and also this error box will be less big. So it will squeeze a lot. You see, this event that before was covering all this part of the sky now is reduced to tenths of square degrees. Okay? For each of the detection that I will show you, and for entire population of the binary black hole, binary neutron star, binary black hole, and neutron star, we had a follow-up campaign. Of course, I cannot report all the results. The one I will report are the ones that are more meaningful, but I want to show you, at least for the first event, what is the chain. So we have seen that there was a follow-up campaign that unfortunately for that event didn't bring any additional information on the counterpart of the source. And associated with each of these events, we have a dedicated analysis that is looking for neutrinos. So why are we looking for neutrinos where there are 2 binary black hole coalescence? I don't expect neutrino from that. Are we out of our minds? Probably. So the point is that you have to assume that at least one of the black hole has a surrounding disk around. So that's the only way in which the neutrinos can be produced, okay? Through the shock wave and the interaction with the dust and the accretion disk around, they can be produced. So saying that, the two neutrino detectors that were in operation during the first ever detected gravitational wave event were Antares, that is in the Mediterranean Sea, in front of the French coast, and Ice Cube that is at the South Pole. Tomorrow we will talk about them in a bit more detail. And so you see what you the result that you have is the sky map, in which you have this elongated shape that is the one associated with the gravitational wave event, and the crosses that you see are the neutrinos that have been constrained in the same time at which the event was happening in the gravitational wave interferometer. So we did have a coincidence in time, but not in space. So we cannot assume that these neutrinos and the gravitational wave are coming from the same source, okay? So unfortunately, we didn't find any association with, between the neutrino and the gravitational wave in this case. Same happened for the Box Day event and the Boxing Day event and the candidate. Again, what you will see is the sky map in which you have the error region of the gravitational wave event. If you have two error regions, it means that only two detectors have seen the event, and then the crosses that are the neutrinos coming from Ice Cube or Antares. Okay, so this is the beginning of a really great adventure in which for centuries we have only the studies of X-rays for black holes, and now we see not only a binary system of black holes, and for each of them we can study three different compact objects, so the two that merge and the final one, but also we are discovering that they range in a different mass range. That was one of the unexpected news, considering the fact that these systems are binary systems. Okay, and the other difference, of course, related to the parameter of the system, the mass, the spin, and so on, that we covered the other day, is the fact that each of these waveforms that we discover is peculiar. So we don't have a waveform that is equal or similar to the other. And you see, this event was only less than half a second, the first event, in the gravitational wave band. This candidate event was a bit longer. The second detection was almost 2 seconds, a bit less than 2 seconds, and this one, that was the first one of the second observing run, it's 0.25 seconds, okay? And of course, the feature of each of these gravitational waves is important when you have to consider that you have the sensitivity bulk of your detector, and so that will play a role on the time and the frequency at which these waveforms will stay in your detector, and so the time that actually you can use to try to catch them, okay? You see, this one, the first one, it was pretty high in frequency and arrived till 200 hertz, but the second one was even higher, arriving to 1,000 hertz, okay? So also the amount of the frequency bulk that they are covering, it's also different. The other way in which you can see the detections is the amount of detection horizon that you can cover from where you are. So we are on Earth, we are here. The first detection was about 1.3 billions light years away, and the second event was more or less at the same distance, 1.4 billion light years away. But the first of the second observing run, so in which we already upgraded a bit the detector, was already at 3 billion light years away. And so every time you upgrade the detector, you gain in sensitivity, and so the detection horizon scales with it. Of course, the first detection and also the other two were a really spectacular event, and these are some of the papers that we publish. And as you know, Ray Weiss, Barry Barish, and Kip Thorne have been awarded with the Nobel Prize in 2017 for the discovery of these amazing astrophysical objects. Okay, so what I will do in the following is that we have a population of 90 detections, and so I will pick the one that are most significant because they show some particular feature or something that we didn't expect it. I cannot cover 90 detection because we cannot stay here till tonight, but I will try to give you an overview of the most impressive detections that we have. So let's start with the 1708-14. So during the second observing run, the Virgo detector joined the run during the last month, so August 2017. And the 14th August 2017, that was the first triple coincidence event that we have seen. And this is the event, the signature of the event, as was seen in Hanford, in Livingston, and Virgo. Of course, you have here you have the SNR over time. You in the central plot you have the frequency over time, and in the lower one you have the reconstructed strain over time. So let's see what happened in terms of the error region associated with the event. So you see this banana shape is the one produced by the two LIGO detectors. Then if you add Virgo, what happens is that the region that you have to take into account, it's only the green one. And so the amount of square degrees, it's almost around 60. The other shade region that you see is the one that was the final localization of the event during an offline analysis. So while the yellow and the green were done online, so passing through the data and sending out the alert to see if there was any counterpart associated with the event. So you see, in comparison with the other gravitational wave that we already seen, this event is pretty small in the error region. It's really a good improvement. And so you see that the fact of having 3 detectors that are reasonably well behaving at the same time is the perfect things that you can ask for. And then 3 days later, we had an astonished discovery. So the discovery of the binary neutron star system that per se would be already wonderful, but we were extremely lucky. And so on top of the discovery of the first ever binary neutron star system, we also have a plethora of electromagnetic discovery associated with the same event. So let's see what does it look like. So these are the two neutron stars orbiting each other. The mass is 1.4, 1.3 more or less. Then they merge. They create a kilonova with the electromagnetic emission, and then there is the creation of the final compact object. So what we just saw is the coalescence of the two binary neutron star, and you see that the gravitational wave signature lasted about 100 seconds, so much more compared with the one that we saw before. Then what you have seen in the video is the production of the short gamma ray burst in the region of the sky that was overlapping with the two coalescence of the neutron star, and also that this merged object produced a kilonova. That is a nova, but is 1,000 times brighter than a normal nova, like the one that Alicia was explaining to you yesterday. So let's see. This is the data coming from the three different detectors. You have on the top M4, Livingston, and Virgo. So what you will see in the time frequency is the usual signature that you expected in a bit. 0 is the coalescing time here, so you have to arrive till the end. Okay. So these are, and it's so loud that you can see it also by eyes, by naked eye. And this is instead what happened to start the revolutionary follow-up. So the bell that you hear is not other than a common, apparently, gamma ray burst with the same name. You see 170817A. That was detected by Fermi exactly in the same direction. And so that was the first association that we had just 1.7 seconds after the signal of the gravitational wave. This is all pretty nice, but that's what actually happened in the Livingston detector. So you see in the left plot, what you have is a time frequency plot in which you can still see the signature of the waveform that you expected, but on top of that, you have a huge glitch. And that's the reason why the online analysis that was ongoing at the Livingston site didn't pick up the signal because there was the glitch. So you just relax, calm down, and try to fix what you're facing. So what we said, you have to remove the glitch that you know is a glitch. So what you do is you produce this plot in which you have this strain over time, and you see that clearly here in the time frequency in the time series there is an event, and this one instead, the blue one that probably I'm not sure you can see, is the glitch model. And so once you identify the issue, you are able to remove it. And when you remove the issue, so in this case is the glitch, you can reanalyze the data and confirm that actually you have an event there. Okay? And so you can then show to the world that you have done well your homework, you knew what was the type of glitch that was happening at that time, and due to the fact that you were able to remove the glitch, you can easily reconstruct the waveform of the event. In this, yeah, sure. That's one of these cases in which Virgo is in the blind spot. So it's the event was one in one of this blind spot of Virgo, and as we said, it's anyway a great indication for the localization of the event, because it's exactly the same as seeing the event triangulated in that position. Thanks for the question. And so, since we have a 3 detector detection, you should have, so you expect, an error region associated with the detection that is pretty small. In this case, it's one of the most wonderful one, because it's only 28 square degrees. And here you have one of the common plots that we used to show, in which you have the reconstruction of the 2 masses of the binary system, in this case, the binary neutron star. And so when you look at this plot, what you have to pay attention on is this shape, in which you have the combination of the possible masses of the system. And of course, how do you choose? You choose through a probability, like a likelihood, and the different color, the blue and the red, is related to the fact that we wanted to analyze whether they have a low spin or an high spin. So these are the parameters that are published in the paper, and you see the binary neutron star had the primary mass that has 1.36 solar masses, and the second one that was almost 1.2. Then we have the shear mass, the mass ratio, and so on, and the luminosity distance is 40 megaparsec. So this is a bit adding a bit more information. So here you have the light green is this banana shape, and this banana shape are the one reconstructed by the 2 LIGO detectors. So that's why you have 2 error regions that are associated with the same event. Then Virgo comes to play, and so you have only 1 error region, and the error region is smaller in comparison with the other one. Then fortunately also Fermi and Integral were looking at the same event, and so you have this shaded light blue curve, and the Fermi GBM instead had this superimposition of the region. And so the first detectors that was able to identify the galaxy in which this event was produced was SWAP, that is an optical telescope that localized the galaxy in which this beautiful event happened, and that was 11 hours after the event. Of course, we have several optical telescopes, the LT Vista, then the X-ray, the radio telescope. Once the host galaxy was pinpointed and is the NGC 4993, then everybody was able to get the information and in the image of what was going on with this really impressive event. And so you see here apart from the name of the different detectors that have been following the event, you have the time scale. So this happened in the optical, it happened few hours after the event, so 11 hours more or less. Then we have to get a clear view in the X-ray, we had to wait 9 days, and the radio was even longer, was almost 17 days. And what we have seen is this the formation of the kilonova, that is this bright source that we observe from the ultraviolet to the optic, infrared, transient, as the decay of these heavy elements that are formed in the neutrocarapton. So that's why you see the brightness versus the wavelength in this plot that is going from the blue range to the red one. Is none other than the decay of the heavy elements when time passed by. And so this is the first confirmation of the connection between the merger of a binary neutron star with the formation of a kilonova that result in this radioactive decay of heavy elements. And so here again you can see what happened. The bright source that is the kilonova. That's exactly the day of the event, and here a few days later is getting fainter and fainter. So it's exactly the decay of the heavy elements that you have seen. This one from the blue to the red. Okay, so thankfully, the observation, the follow-up campaign was pretty wide, and we got all the detections in coincidence with the gravitational wave event in electromagnetic spectrum, from the optical to the X-ray, ultraviolet, radio, and X-ray at the end. What about neutrinos? Unfortunately, that's the missing link. So here you see one of these sky map that I also showed you before. This one is the black cross is the location of the host galaxy, so the NGC 4993, and the red area that you see is the error region of the gravitational wave event. This is the line of sight of Antares. This one is the line of sight of Ice Cube. And you see, in a time interval related in coincidence with the event, we were able to get few neutrinos, but not from the direction that we expected. So we have seen this event in all the electromagnetic spectrum. We have seen all the coincidence events in the electromagnetic spectrum. What's missing is the neutrino detection associated with that. Okay, what else did we learn? So due to the fact that the gravitational wave and the arrival time of the gravitational wave and the gamma ray bars was not the same, there was a delay of 1.7 seconds, what we could constrain was the speed of the gravitational wave in comparison with the light. And as you can see, they are not really much different, because the constraint is between -3 times 10 to minus 15 and +7 times 10 to minus 16. So you can say that that they go at the same speed. Another thing that was extremely important to test was through the electromagnetic follow-up and the fact that that we have seen the kilonova is the variety of models that we have connected to the electromagnetic signals. And so since we have seen the decay of heavy elements from the blue to red, one of the model that is the classical one that we consider is the preferential one is in this case, and is the so-called cocoon model. What else? Well, cosmology will say that if we use this gravitational wave event as a standard candle, and so since we detected the luminosity distance and we know the redshift, we can compute the Hubble constant. And in this computation, what we have is that the value that we got is completely in agreement with what Planck found in his result. So we are extremely happy of the agreement. Another thing that that was important to test is the constraint on the equation of state of the neutron star that you can have. Of course, what you do is you test the event that you detected with a series of different equation of state. They can be steeper or less steep, but what you get is an hint on the description of the density of this neutron star, and in this case, the binary neutron star. So in this case, the preferred model is a softer model, soft in the sense of the parameter of the equation of state that regulate the compact object. This is one of my favorite way to visualize the detections, because here you can see on the vertical axis you have the masses of this compact object, and you can definitely see that for each of these event you have to study 3 different bodies. So this is one of the configuration. Here you have the blue that you see are all the binary black hole detections, and here instead you have the binary neutron star. So here is to show you once again what happened when we have a triple coincidence of the same gravitational wave event. So in comparison with the other events in which the error region is really huge, you have a reduction in the error region that is the easy way to go when you want to follow up the complete region associated with the event. We released 4 different catalogs because on the way we realized that some of the candidates were reclassified, and so during the first catalog we released 11 confirmation of the event. Then there was the second catalog that was on the first part of the third observing run, and it contained 39 confirmation of binary black holes events. But then we realized, analyzing the data again, that 3 we have to reclassify, and so they didn't meet anymore the threshold limit. But we also have 8 new events that we didn't see straight away, so they were hidden in the noise. And so with this we come up to a value of 55 total events, and then we have to add 35 events in the second part of the third observing run. So this stands for gravitational wave transient catalog, and the numbers are associated to the different runs. So the first one is for the first and second observing run, and for the second one you have part of the the first part of the third run, and then the second part. And these are the dates that span for the runs. This probably we have seen it already, but it's just to point out that the sensitivity at the binary neutral star range was not always the same for all the detectors, and so you have 4 bars, one for each observing run. So the first one is O1, the second one is O2, O3A, and O3B. So this is another way to display the different detections. So these are 10 binary black holes and 1 binary neutron star. And when you go on, you increase the number of sky maps that you have in your slide, and then you cannot put them anymore in it. One thing that I really like is this cartoon of the different detections in which you can really realize the difference in mass, how they spin, how they behave and orbiting each other. And the other thing that I want to point out is that after the second observing run, we slightly changed the naming of the event. In fact, we realized that we could have 2 or more events in the same day. So in the case of a real event, they will not get the same name. So what we decided was to have GW, the date, so year, month, and day, and then the UTC time, so that they are identified in a unique way. So this is what happened for the first 2 observing run. This is the result with the O3A run. This, as in every group, as we see in a second, will be the party crasher. And we said that it's possible through this observation to get not only the estimate of the masses and the final mass of the compact object, but also the spin, and try to understand how squeezy the neutron stars are. So these are all the observation that we have, 90 observation. This one, light blue, is O1, orange is O2, and all the others. This is O3A, this light color, and the darker one is O3B. So we have seen the first detection, the revolutionary in the gravitational wave field, the one that was awarded with the Nobel Prize, and that we have seen the extraordinary detection of the binary neutron star, followed by the detection of the counterpart in the electromagnetic spectrum. So let's go on and see some particular feature that we have seen in this population. So there is this one, GW190521, is a black hole in the pair instability. So this is the plot show again the reconstructed waveform on top, on the top row, and on the lower row you have the frequency and the time. And so you see the signal is really short in time. It's about 0.1 sigma, 0.1 second, sorry, and it's peaked at really low frequency. So it's less than 100 in frequency. You probably remember then the time interval that the signal spans in the sensitivity band of the instrument is inversely proportional to the total mass of the binary black hole, and the same goes for the frequency. So let's have a look at the parameters. So the primary mass is estimated to be 85 solar masses, and the secondary one is 66 solar masses. So why is that an issue? So this one is the same plot I showed before, and you remember on the vertical axis there is the mass scale. So the resulting compact object is the more massive black hole that we ever saw, and it should not exist, because according to star evolution, we should not have black holes in binary system in a range between 100 solar masses and 1,000 solar masses. So it shouldn't be there, okay? On top of that, one of the progenitor should not exist as well, because it is in the so-called mass gap. That means that it's not allowed, so it cannot be formed through stellar collapse. So we have two issues related with the same detection. What do we do? So we try to find. It's of course a challenge, because it's not a standard group of binary black hole that you will encounter, and so you have to find a physical solution for what you are looking at. Of course, they exist. We detect them, so there has to be an astrophysical formation channel for this type of object. And the result is the fact that probably this kind of system was originated in galaxies in which the amount of black holes is really high, and so probably they are all in a dense environment in which it's easy to get the collision of black holes and also get the resulting one that is bigger than the previous one. And so with this line of thinking, what you say is that the only way this can be possible is the fact that these black holes are originated in dense clusters of stars, and not through stellar mergers or hierarchical mergers. Of course, you can have more exotic scenarios, but this is the most plausible one. So just to summarize, this event was also the most distant one ever recorded, 7 giga light years away. And you see this is what we computed to be the angular momentum, so the effect of the spin in the orbit of the two black holes. And we have both the issue of the progenitor and the final black hole that is not supposed to be there. And so that's if with O4 we get more of these events, we can constrain even better the hypothesis that we have done for this event, and maybe find a new way and highlight the fact that it's not correct, of course, that we should not expect black hole in that mass gap in astrophysics. The additional information related to the same object is the fact that the Zwicky transient facility scanned part of the error region of this event, finding an electromagnetic flare. Unfortunately, this at a second look, that wasn't completely consistent with the position of the binary merges, and so it was ruled out as a counterpart. Another interesting tool that you can find is this one, in which you have the usual secondary mass over primary mass scheme, you can go with the mouse and it will highlight the information. This is the event that we just consider. So 1905-21 is giving you the mass, is giving you the time of at which the detection happened, and also the public data related to that event. So let's go to another interesting one, GW 1904-12, that is an equal mass binary. What does it mean? This is, again, the usual time frequency plot that you have. So this system is composed of a binary black hole of 30 solar masses and another one of 8 solar masses. And this, since it's so not symmetric, you can have additional information, and you can constrain. You cannot have additional information. You can constrain better some parameters, like the spin and the behavior of the black holes. And so, due to this object, for example, we can constrain the fact that the primary black hole was spinning about 40% of the maximum allowed velocity that is possible by general relativity. What else? 1908-14. So this is the coalescence of a stellar black hole, so one that is created by the stellar formation, and a mystery object. What does it mean? So here you have already an hint. So it's the same thing that we discussed for black hole, but applied to neutron star. So also in the case of neutron star, so really low masses above 2.4 until 5, there is a mass gap for neutron star. And so this binary system is composed of a 23 solar masses black hole plus a companion mass that is called mass gap, in the sense that is highlighting the fact that is in that region of masses that is order of between 2.5 and 3 solar masses, and is 1,800 million light years away. This is the event that we are considering, and you see here there is, I don't know if you can see it, but there is a question mark, in the sense that we really know what's going on. So this is the event. It was a really loud, extremely loud event, and is again an not symmetric binary system, because one is 23 solar masses and the other one is almost 3. And so we don't know whether the second object is the lightest black hole ever detected or is the heaviest neutron star ever detected. And at the moment, we cannot rule out any of the two. The mass of the object is comparable with the final object that was created in the binary neutron star merger. And so the challenge will be to continue to see this kind of detections and try to figure out whether this is actually a black hole or a really heavy neutron star. Also, in this case, there were a lot of follow-ups, but we couldn't find any electromagnetic counterpart. So this is the, sorry for the quality of the image, I couldn't find a better one. This is the noise over the time of this event. And so we have hint that suggests the possibility that this mass gap compact object is more likely to be a black hole, but we can actually, with the probability that we get, we cannot rule out the fact that can be an heavy neutron star. So we are still in the doubt. That's why in the previous plot there was the question mark. Okay, so these are two the only two events, binary mergers, that we have, in which we have a black hole and a neutron star, and you see they are 10 days apart. So let's see them in detail. These are the two events in the stellar graveyard. So on the left, you see the 200105 that was detected by Livingstone and Virgo. And 10 days later, you have the other detection of this kind of binary system, 200115. The masses are rather, so there is the primary, that is either 9 solar masses, that is a black hole, or a 6 solar masses, that is another black hole, and the companion in the first case is almost 2 solar masses, and in the other case is 1.5. And the distance are slightly different. In the first case, we have 800 million years ago, and in the second one, we have 1 billion years ago. And here you have again the plot in which you see the secondary mass over the primary mass, and these are the point, the correlation of the 2 points that can produce that binary system. How did they form? We have 2 possibilities. So we have the isolated binary evolution, in which the 2 stars orbiting each other explode in a supernova, and so one became a black hole and another one a neutron star. Or we can have a dynamical interaction. So the neutron star and the black hole formed separately, and then afterward they find each other. Was this the difference? We can try to discriminate the 2 time of formation channel studying the spins. So in the first case, in the one of the isolated binary evolution, the spin direction of the black hole tend to align to the companion and to the binary orbit. And so what we expect is that the neutron star will orbit on the equatorial plane of the black hole. In the other case, the one of the dynamical interaction, we don't have any preferential direction of the spin. And so what happened is that the neutron star could have any orientation and any orbit around the black hole. What did we find? So in the here you have the common way in which we used to show this information. So you have this half disk. On the left you have the first event, on the right you have the second one 10 days later. And so the radius of the disk goes from 0 to 1. 0 means no spin, 1 means the maximum rotation rate. And then what you have is that the spin direction is showing in an angle between 0 and 100 degrees. So 0 means that the object spins in the same direction as the orbit of the binary. Instead, 108 degrees means that the object spins in the opposite direction of the orbit of the binary. So let's take the first case. In the first case, we don't have a clear evidence, in the sense that these shadow lines that you see here are near the center, and so that means that in the case of the GW200105, the black hole has a spin that is likely really small. In the second case, what you have instead is that the the black hole, according to this scheme, the black hole may be spinning in the direction opposite to the orbital motion. So so what it's saying is that in the second case, we can point to the dynamical interaction, since we didn't find that the directionality of the spins were aligned. Okay, approaching the end. So this is the 90 events that we have seen so far. Since I still have a few minutes, I want to set things straight, in the sense that in the last two lessons I had question about no, sorry, I didn't finish yet. So the last thing that I want to point out was the population study that we have done. So in this case, what you see here is not the complete set of binary neutron star and black holes and black hole neutron star that we have seen, but only a set of 74 that includes 70 binary black hole to the two binary neutron star that we have in the two neutron star black hole binary. And so you see this plot is similar to the one that I showed you when I was explaining the different template that we use for the match filtering. And so this plot is getting populated, and we have seen some of the feature of these events. And when we performed the population study, because we wanted to get an hint on the or solve, for example, the issue related with the mass gap, both in the case of the black hole and the neutron star. Unfortunately, we didn't get any precise indication. What you see here is on the vertical axis, the differential merger rate of the primary mass. And on the horizontal axis, you have the primary mass in solar masses. And so you see these, the lines and the shadow region that you see are the different models that we use that are different in the sense that consider different parameters, and so to try to be flexible to reproduce the population that we detected. And so as you see, we can identify different bumps related to certain ranges of masses for the primary mass. And so, as I was saying, we don't have a confident identification of the presence either of the mass gap for the binary black holes or for the same mass gap for neutron stars. So what we need is to get an ensemble of detections that is much bigger, and so we can try to exactly identify the mass ranges at which these happen. Okay, so these are just for memory what we have done. So we detected the gravitational wave. We're really extremely happy with the first event, but then the unexpected happened, and we were even happier than before. And so right now we are at 90 detection. Yesterday we have seen that we expected a number that should be around 170 new detection for in the next 20 months. So coming back to what I was briefly mentioning before, yesterday I talked about the future of the terrestrial, the ground detectors in the interferometers, and I didn't mention any space detectors. So I want to show, first of all, the fact that in the gravitational wave spectrum, if we compare the ground interferometer with the space one, they are looking to a different variety of astrophysical events, and also different frequency range. Yesterday we have seen that with the ground detector and due to the seismic noise we are not able to go below 1 Hertz, but they will go much below, so in terms of 10 to minus 4, 10 to minus 2 in the bucket of the sensitivity. And as I said yesterday, one of the best detector that we will have it's LISA, and this is the result of LISA Pathfinder. So see, it's really impressive because here you have the strain, and here you are on the vertical axis, and on the horizontal one you have the frequency. This is actual data. So here you have the data coming from April 2016. There was already approaching the requirement to build the detector. And then what happened next was that they were able to let the detector behave even better, and not by a small factor. So take a look at this impressive result. This is the last data taking of LISA Pathfinder that started the actual construction of the detector. And that would be the final configuration. So this gravitational wave detector will be in space. There will be three different antennas in this triangular shape. The length of this triangle will be 50 million kilometers. Will be 2.5 million kilometers. The 50 kilometer is the distance from Earth. And what they will do, they will orbiting each other and try to detect the gravitational wave from a supermassive merger of black holes, of binary black holes, and also binary white dwarf in the Milky Way. The plan starting of the operation, and of course the launch of this detector will be 2034. Okay, so I think I will stop here and I will take any question you have.
Thank you very much, Irene, and also reminding that next week we're going to have lectures by Zoltan Hyman about the astrophysics of black hole mergers. So many of these issues, they will appear again. So, questions for Irene here? Okay.
Hi, great lecture as always. I was just wondering, because you said you were curious about collapse supernovae, and
tomorrow I will talk about that.
Oh, tomorrow you're going to talk about, okay.
Yes. But not collapse of binary, collapse of supernovae, just, not in binary systems.
Right. And just another question, because I saw you didn't comment, didn't make any comments. I just like to hear your thoughts on like nanograv and pulsar timing arrays. How, what do you think about that, and what sort of frequency domain does that explore?
So it's over here. It's even pushing the boundary of frequency even more than the space detector. This is another impressive effort that is going on, and I think when the different collaboration will finally sit and talk to each other, it will be impressive the amount of science that we will discover. And so the frequency range is the nanohertz more or less. So it's 10 to minus 9 hertz going down. Yeah, you can discover cosmic strings, binary system, primordial binary systems. So everything that goes to the relic of the universe, you will be able to see with these detectors.
Thank you again for your presentation. Regarding the black holes with very high mass that you mentioned,
the particle pressure. Yeah.
Yes, you mentioned that it is possible that they are coming from a hierarchical merger, sequence of mergers, or perhaps an exotic mechanism. But I was wondering if it is a possibility for you that experimentally you are measuring or overestimating these black hole masses in a systematic way.
Why do you say so? I
No,
mean, do you?
I just was.
No,
I
no,
was
no.
wondering.
I would like to understand the reasoning. So, of course, it's possible that something is wrong. In this case, as always, we check with different pipeline, and everything seems to be in agreement. So I don't think that the mass are wrong.
Okay, no,
The
I just
estimate of the mass. I
I
don't
was
know if
wondering this just
maybe you
because.
were thinking to a particular process that we didn't think
No, no,
of. And
no, not a particular process. Just because you mentioned that for the case of the neutron star,
Yeah.
you would have a very heavy neutron star, or
Yeah.
if this were the case,
Yeah.
and also for this 150
Yeah, 50 of 45,
black hole.
yeah.
In both cases, you have heavier masses than expected, right?
Yeah, but in that case, the only compact object that can appear is a black hole. So that object has to be anyway a black hole. The discrepancy in the other case is the fact that you are in the lower band for the black hole and in the higher mass range for the neutron star, and so you have the possibility of thinking that in one case can be the lightest black hole or the heaviest neutron star, but for this guy here can be only a black hole. So the question is, we need to find out what is the exact, we need to find a solution to understand what was the process that allowed us to see such an event that we didn't expect through stellar evolution.
Okay, thanks.
It's interesting that in astronomy, we are usually obsessed with selection effects because of the way in which you observe things. But for gravity waves, first, the universe is totally transparent.
Yes.
And
that's the beauty of it.
The only thing you have to worry about is the sensitivity in some sense, and of
Right.
course, how you detect things. So it's a kind of a different exercise in thought.
Hi, thank you for the lecture. I have a couple of curiosity, I would say. How would you define the characteristics of the objects that you are detecting? Because, I mean, you said that the actual detectors that we have nowadays are in the high frequency. So we can only detect the high frequency gravitational waves, the part that is in the merge phase, right? If you have a binary system, it is already you already have the gravitational waves because they are spinning in the space-time, and then you have the merge phase, which we have the higher amplitude of the gravitational wave, and then you have the ring-down phase when the frequency decreases a lot. And in the ring-down phase, if I'm not mistaken, is where you have the quasi-normal modes, which are used. I mean, I think you used to calculate the properties of the binary black hole or neutron star, whatever. So, I mean, what is the process you use to calculate these properties if you don't have access to the high frequency of the gravitational wave? You use some sort of, I don't know, guess of the rest of the gravitational wave?
So I've said that you can only detect the gravitational wave signal coming from this binary system of compact object when they lie inside the sensitivity band of your detector. That doesn't mean that you only see the high frequency range of this signal, because the first for example, the first one of the first binary neutron star, binary black hole that I show you, it was the one with really high masses, but there was really low in frequency. If you remember, if I can get to the slide, it was order of 50 Hertz, and so it wasn't high to be a binary black hole, and that's due to the waveform itself that is produced by the system is characterized by the fact by the different parameters that describe the system, so the mass, the spin, and so on. What we do to see, this one is between 50 and 70 Hertz. So it's really low in frequency.
So you detect all the waveform, not
yes,
only the
inside,
ring down.
yes,
Okay.
inside the sensitivity band of the detector. And so what we do is first we want to be sure that we have a detections, and so we have multiple pipelines, bless you, doing the same thing, and so trying to characterize the waveform. And then we have a separate effort that is going into parameter estimation. So what you do usually is you use the template waveform that you use for the match filtering, in which you have the characteristic of the several parameter, the mass, the spin, the one that are the intrinsic parameter of the binary object. And so you find the waveform that better characterize the signal that you have.
It was a nice question, because how could you differentiate the properties of of the black hole from the neutron star? Like, how can you estimate the mass of each one if you only have the final?
So in the case of the neutron star, you have two additional parameters. So in the case of the binary black holes, we have 15 parameters. In the case of the binary neutron star, you have two more. So the tidal deformation of the neutron star when they spiral each other. And so from there, you can also get the information about the distance between the two objects that were spiraling, how was effective the first mass on the second one, and so on.
Okay, but how the problem with the number of parameters is involved in this? Because you said, I think yesterday, that we cannot have that many parameters when we are calculating it, but you have to have them to estimate the characteristics. So
yeah, it's a refinement problem. So you find the waveform in which you define you match, for example, the masses of the binary the binary system, and then these are fixed, and then you go on. You find the
try
spin.
to match it the best way you can.
Yes,
so,
of course. And that's why when I talk about the spins, I always give you the probability in percent that you can have. It's not anything is certain, but you have the probability that was the case.
Okay, another question. I think last questions before we break, okay?
So can you please tell me about what is the strength of this signal?
I'm sorry.
The strength of this signal.
The strength of this one?
Yes, yeah.
What information do you want?
The strength, like the power strength, something like that, of this GW signal.
Total mass. Let me see. You want the amount of masses that were released during the merger, right?
I don't know. My second question is like, so far, whatever we have detected from only from the binary system. So what do you think about the GW from multibody system, like 3 black hole, like something like that?
My opinion, my personal opinion, I don't think that this kind of systems will last long, in the sense that if you have a system that can can afford 3 black holes, maybe 2 will survive, if not 1, because in that case, I mean, you have to conserve the energy, but also the fact that if they are in binary system, it will be really difficult to obtain a system with 2 binary and 1 in common. I don't think that will ever happen, but that's my personal opinion.